The switch has been closed for a long time in the below circuit. How much energy in joules is stored in the fully charged capacitor? Let's first examine what's going on. When a capacitor is fully charged, there is no current flow through it. So the current comes out of the battery here, goes here, and if we just had this piece of the circuit, there would be no current because this potential would exactly match this potential but be in the opposite direction. However, we have this junction point here. So current will flow like this because that switch is closed and come on down here. So what does that mean? Well, we have a current and we're going to solve for that in a second. There'll be a voltage drop here. So this will pick up part of the voltage drop from the 6 volts. The capacitor will pick up the other piece. So let's see what we're talking about here. If I just showed you a circuit that had a 2 ohm and a 1 ohm resistor in series, which is what that is after a long time, you would find the equivalent resistance, which is 3 ohms. You would find the current through that path, which would be the 6 volts of the battery, divided by 3 ohms. You'd have 2 amps flowing through this purple loop here. So let's look, what is the voltage difference across this 1 ohm resistor now? Well, it's IR, 2 amps times 1 ohm, which is 2 volts. Who's in parallel with the resistor? The capacitor. So this capacitor also has 2 volts across it when it's fully charged. Where are the other 4 volts? Well, they're being dropped here, right? The current is 2, so V equals IR. 2 times 2 is 4 volts. Now, to find the energy in the capacitor, the potential energy stored, 1/2 CV squared. C is 3 millifarads. We've got the 2 volts here because it's in parallel with this resistor, and we have an energy stored of 6 millijoules.